Why is the first BIOS instruction located at 0xFFFFFF0, top of RAM? I know that BIOS loads its first instruction from 0xFFFFFF0, but why this specific address? I've a bunch of questions and hope you can help me with some of them, at least. My questions. Why is the first BIOS instruction located at the top of a 4 and NBSP, GB RAM? What would happen if my computer only has 1 and NBSP, GB of RAM? What about systems with more than 4 and NBSP, GB of RAM, for example, 8 and NBSP, GB, 16 and NBSP, GB, etc.? Why is the stack initialized with some value, in this case, a value located at 0xFFFFFF0? I've read about that this afternoon, and I still don't get it.
.0xFFFFFF0 is where an x86 compatible CPU starts executing instructions when it's powered on. That's a hardwired, unchangeable, without extra hardware, aspect of the CPU, and different types of BIOS behave differently. Why the first BIOS instruction is located at the top of a 4 and NBSP, GB RAM. It's located at the top of 4 and NBSP, GB address space, and on power on the BIOS or UEFI ROM is set to respond to reads of those addresses. My theory on why this is. Just about everything in programming works better with contiguous addresses. The CPU designer does not know what a system builder will want to do with the CPU, thus it's a bad idea for the CPU to require addresses smack in the middle of the space be required for various purposes. It's better to keep that out of the way at the top or bottom of the address space. Of course, keep in mind this decision was made when the 8086 was new, which did not have a MU. In the 8086, interrupt vectors existed at memory location 0 and above. Interrupt vectors need to be at known addresses and were desired to be in RAM for flexibility, yet it was not possible for the CPU designer to know how much RAM was going to be in a system. So starting from 0 and working up made sense for those, because no system in 1978 when the 8086 was invented would have 4 and NBSP bytes of RAM, so expecting RAM to be at 0xFFFFFF0 was not a good idea, and then ROM would have to be at the upper boundary. Of course, starting with at least the 80286, interrupt vectors could be moved to a different starting location other than 0, but modern 64-bit x86 BIOS still boot up in 8086 mode. So everything still works the old way for compatibility, as ridiculous as it sounds in 2015 to still need your x86 CPU to be able to run DOS. So since interrupt vectors start from 0 and work upward, ROM would have to start from the top and work downward. What would happen if my computer has only 1 NBSP, GB of RAM? A 32-bit CPU has 4,294,967,296 addresses, numbered 0 by 0000000 to 4,294,967,295, 0xFFFFFFF. ROM can live in some addresses and RAM can live in others. With the CPUs, this can even be switched on the fly. RAM does not have to live at all addresses. With only 1 NBSP, GB of RAM, some addresses will not have anything responding when they are read or written to. This can cause invalid data to be read when such addresses are accessed or a system lockup. What about systems with more than 4 and NBSP, GB of RAM, e.g., 8 and NBSP, GB, 16 and NBSP, GB, etc.? Keeping it somewhat simple, 64-bit BIOS have more addresses, which is one of the things that makes them 64-bit, for example 0 by 00000000000000000 through 0xFFFFFFFFFFFFFF, for example, so the extra RAM fits. Assuming the CPU is in long mode. Until then the RAM is there, just not addressable. Why is stack initialized with some value? In this case, a value located at 0xFFFFFFF0. I can't immediately find anything on what x86 assigns the stack pointer at power on, but it would eventually have to be reassigned by an initialization routine anyway once that routine finds out how much RAM is in the system. At Eric Towers in the comments below reports that it is set to 0 on power up.
It isn't located at the top of RAM, it is located in ROM whose address is at the top of the memory address space, along with any memory on expansion cards, like Ethernet controllers. It is there so that it won't conflict with RAM, at least until you have 4 and NBSP, GB installed. Systems that have 4 and NBSP, GB or more of RAM can do two things to resolve the conflict. Cheap motherboards simply ignore the parts of RAM that conflict with where the ROM is located. Decent ones remap that RAM to appear to have an address above the 4 and NBSP, GB mark. I'm not sure what you are asking about the stack. It certainly isn't initialized to be in ROM. When the CPU resets, it is initially in real mode, where it acts just like the original 8086 and uses 16-bit segmented addressing, allowing it only to access 1 and NBSP, MB of memory. The BIOS code is located at top of that 1 and NBSP, MB. The BIOS picks somewhere in RAM to set up the stack and loads and executes the first sector of the first bootable drive. It is up to the OS to switch into 32 or 64-bit mode once it takes over and set up its own stacks, one per task/thread.
First, this has nothing to do with RAM, really. We're talking about address space here. Even if you only have 16 MB of memory, you still have the full 32 bits of address space on a 32-bit CPU. This already answers your first question. Really, at the time this was designed, real-world PCs had nowhere near the full 4 GB of memory, they were more in the range of 1 to 16 MB of memory. The address space was, for all intents and purposes, free. Now, why 0xFFFFFF0 exactly? The CPU doesn't know how much of the BIOS there is. Some BIOSes may only take a few kilobytes, while others may take full megabytes of memory, and I'm not even getting into the various optional RAMs. The CPU must be hardwired to some address to start on, there's no one to configure the CPU. But this is only a mapping of the address space, the address is mapped directly into the BIOS ROM chip, yes. This means you don't get access to the full 4 GB of RAM at this point if you do have that many, but that isn't anything special. Many devices require their own range in address space. On a 32-bit CPU, this address gives you full 16 bytes to do the very basic initialization, which is enough to set up your segments and, if needed, address mode. Remember, x86 boots in 16-bit real mode, the address space isn't flat, and do a jump to the real boot procedure. At this point, you don't use RAM at all, it's all just mapped ROM. In fact, RAM isn't even ready to be used at this point, that's one of the jobs of the BIOS post. Now, you might be thinking, how does a 16-bit real mode access the address 0xFFFFFF0? Sure, there's segments, so you have 20-bit address space, but that still isn't good enough. Well, there's a trick to it. The 12 high bits of the address are set until you execute your first long jump, giving you access to the high address space, while rejecting access to anything lower than 0xFFF00000 until you execute a long jump. All this are the things that are mostly hidden from programmers, not to mention users, on modern operating systems. You usually don't have any access to anything so low level, some things are already beyond salvage, you can't switch CPU modes willy-nilly, some are exclusively handled by the OS kernel. So a nicer view comes from old-school coding on MS-DOS. Another typical example of device memory being directly mapped to address space is direct access to video memory. For example, if you wanted to write text to the display fast, you wrote directly to address, the 800:0000 plus offset, In 80 by 25 text mode, this meant Y80 plus X, 2, if my memory serves me right, 2 bytes per character, line by line. If you wanted to draw pixel by pixel, you used a graphics mode and the start address of A000 column 0000, typically 320 by 208 bits per pixel. Doing anything high performance usually meant diving into device manuals to figure out how to access them directly. This survives to this day, it's just hidden. On Windows, you can see the memory addresses mapped to devices in the Device Manager. Just open Properties of something like your network card, go to the Resources tab. All the memory range items are mappings from device memory to your main address space. And on 32-bit, you'll see that most of those devices are mapped above the 2 GB, later 3 GB mark. Again, to minimize conflicts with user-usable memory, though this is not really an issue with virtual memory, applications don't get anywhere near the real hardware address space. They have their own virtualized chunk of memory, which might be mapped to RAM, ROM, devices or the page file, for example. As for the stack, well, it should help to understand that by default, stack rows from the top. So if you do a push, the new stack pointer will be at 0xFFFFFF. In other words, you're not trying to write to the BIOS init address smile, which of course means that the BIOS init routines can use the stack safely, before remapping it somewhere more useful. In old school programming, before paging became the de facto default, the stack usually started on the end of RAM, and stack overflow happened when you started overwriting your application memory. Memory protection changed a lot of this, but in general, it maintains backwards compatibility as much as possible. Note how even the most modern x86-64 CPU can still boot MS-DOS 5, or how Windows can still run many DOS applications that have no idea about paging.
In addition to the other points mentioned, it may be helpful to understand what an address is. While newer architectures complicate things, historically a machine would on each memory cycle output the desired address on 20 to 32 wires, depending upon the architecture, with some special tricks to note whether it needed to a pair or foursome of bytes simultaneously. Various parts of the memory system would examine the state of those wires and activate themselves when they saw certain combinations of high and low values. If a machine with 32 address wires only needed to use 1 MB of RAM and 64 kilobits of ROM, quite plausible for some embedded controllers, it might activate the RAM for all addresses where the top address wire was low, and the ROM for all addresses where it was high. The bottom 20 address wires would then be tied to the RAM to select one of 1,048,576 bytes, and the bottom 16 would be wired to the ROM as well, to select one of 65,536 bytes. The remaining 11 address wires would simply not be connected to anything. On such a machine, accesses to addresses 0 by 001000000 0 by 001FFFFF would be equivalent to accesses to RAM addresses 0 by 0000000 0 by 000FFFFF. Likewise with addresses 0 by 000200000 0 by 0002FFFFF or 0 by 7FF00000 0 by 7FFFFFFF. Addresses above 0 by 80 million would all read ROM, with the 64K pattern repeating throughout the space. Even though the processor has a 4,294,967,296 byte address space, there's no need to have hardware recognize that many distinct addresses. Putting the reset vector near the top of the address space is a design that will work well regardless of how much or how little RAM and ROM the system has, and avoids the need to fully decode the address space.
support kernel, crea se concepe subscripting.